Hello my dear students, welcome to the next lecture in analog electronics. In this lecture we will continue our discussion on power amplifier and classes of power amplifiers. So you can see a public address system where the power amplifier is the final stage which is connecting to the loudspeaker. The early stages build up the voltage level of the signal while the last stage builds up power to a level sufficient to operate the loudspeaker. This is a typical example. Now let us see the difference between small signal and large signal amplifiers. Small signal amplifiers are those amplifiers which handle small input AC signals, which is in a few millivolt or a few millivolt range. Then these are small signal amplifiers. Voltage amplifiers generally fall in this class. The small signal amplifiers are designed to operate over the linear portion of the output characteristics. Therefore, the transistor parameters such as current gain, input impedance, output impedance, etc. do not change as the amplitude of the signal changes. Such amplifiers amplify the signal with no distortion. That is, you get the whole signal at the output. Now, large signal amplifiers are those which handle large input AC signals. So, the power amplifiers will come under this class. The large signal amplifiers are designed to provide a large amount of AC power output so that they can operate the output device like a speaker. The main features of large signal amplifier or power amplifiers are circuit's power efficiency, maximum amount of power that the circuit is capable of handling, and impedance matching to the output device. Now, what are the difference between a voltage and power amplifiers? We have just discussed some of the differences. We'll go into a little detail considering the features. Voltage amplifier is designed to achieve maximum voltage amplification. It is not important to raise its power level. On the other hand, a power amplifier is designed to obtain maximum output power. Then voltage amplifier features, if you go through, the gain of the voltage amplifier is beta RC by Rin. The transistor with high beta is used in the circuit. In other words, the transistors are employed will have in voltage amplifiers will have thin base. The input resistance Rin of the transistor is thought to be quite low as compared to the collector load RC. Now, a relatively high collector load RC is used in voltage amplifier. To permit this condition, voltage amplifiers are always operated at low collector currents. If the collector current is small, we can use large RC in the collector circuit. Whereas in power amplifiers, it is required to deliver a large amount of power, so it has to handle a large current. The size of the power transistor is made considerably larger in order to dissipate the heat produced in the transistor during operation. The base is made thicker to handle large currents. In other words, transistors with comparatively smaller beta are used. Now, transformer coupling is used here for impedance matching. So let's discuss a little more detail about transformer impedance matching, which we haven't discussed in the last lecture for transformer coupling. So for this, consider a simple voltage amplifier circuit. This one which you are already familiar with. In the circuit, the whole VCC will not appear across this transistor. Now, under the quiescent conditions, the DC collector current ICQ, that is ICQ is the DC collector current, it is approximately equal to IEQ. We use this approximation. Then the DC voltage available between the collector and emitter of the transistor, what is that? VCEQ. Between the collector and emitter of the transistor is VCC minus ICQ into RC plus RE. This is the drop across RC and RE. Okay. So a portion of the supply voltage is dropped in the resistors. Now the DC power that goes to the transistor, what is the DC power? PDQ. The DC power that is dissipated in the transistor is VCEQ into ICQ. This is the quiescent condition we are talking about. That is why this Q is coming here. Okay. So this is representing the effective DC input power to the amplifier. Only a portion of this power can be converted by the amplifier into useful AC power when the signal is applied. This is the quiescent condition. Okay. So out of this DC power, some amount of power is converted to useful AC power. Now we'll see why this circuit cannot act as a good power amplifier. So the total DC power which is drawn from the DC sources VCC into ICQ. So out of this, only VCEQ ICQ is the effective DC input power to the amplifier, because some power is dissipated somewhere else. We'll see that. What is the difference of that power? See, VCC ICQ minus VCEQ ICQ. What is that? We should get this difference. We can get this difference from this expression if we multiply this by ICQ. So VCC ICQ minus VCE ICQ will be nothing but, what will be that? ICQ square into RC plus RE. This is obtained from this expression, this first expression which we wrote. Okay. So what does this imply? This much power is getting wasted in the resistors. That is, it is simply heating the resistors RC and RE. Okay, so VCC ICQ is the input DC power. This is the power that is dissipated across the transistor, and this much is getting wasted out of this VCC ICQ. So this circuit cannot act as a good power amplifier because of this drop. As IC is increased to a larger value, when you want to handle larger signals, this RC will cause a drop. So in order to avoid this, we are going for transformer coupling, replacing a transformer here, that is this RC is replaced by an inductor. So the inductor will have low DC resistance, or it is acting as a short to DC, and it is operating or working, or the resistance is considerable when it is in the AC, when to the AC signal only. Okay, so replacing this RC, we have gone for transformer coupled amplifier. So RE is not avoided because RE is significant in as a part of biasing network. If RE is absent, stabilization of the operating point will become poor. So we are going for this transformer coupled amplifier. So this is a single-ended power amplifier where you have replaced RC with this transformer. What is the peculiarity of this transformer? Suppose it has N1 and N2 number of turns. It can be used for impedance matching. Why? Because this the resistance of this speaker, this is of the order of probably 8 ohm typically, if you take a typical value, but at the same time the output impedance of the transistor is of the order of kilo ohms. So if you want to transfer maximum power from this to this, so according to power transfer theorem, you will require an impedance matching here. That is, if you want to deliver more power, then the impedances of these two should match. So output impedance should be same as the impedance of the loudspeaker. So how this transformer achieves impedance matching here? So that we can discuss now. Suppose RL dash is the impedance seen from the primary side, and N1 is the number of turns in the primary side, and you have N2 number of turns in the secondary side. RL is a load which is connected here. Okay. We can find the ratio of primary resistance to the secondary resistance. How can you find that? RL dash divided by RL. What is that? V1 divided by I1 is RL dash, and V2 divided by I2 is RL. So in that case, if you write it in the voltage ratio form, V1 by V2 into I1 by I2. So as far as the transformer is concerned, what is V1 by V2? It is N1 by N2, and this is I2 by I1. And I2 by I1 is again N1 by N2. So you get the ratio RL dash by RL as this is equal to N1 by N2 the whole square, or this primary side impedance will be N1 by N2 whole square into RL. So by using a step down transformer of appropriate turns ratio, that is N1 by N2, we can match a low resistance RL with a high output impedance R0 of the transistor. So that is how this transformer is providing impedance matching. So as an example, if you consider, if you want to match a 16 ohm speaker load to an amplifier, so that the effective load resistance is 10k. If you want to match it with a 10k, that is the output impedance of the transistor. So if you want to match this, what should be the transformer turns ratio? If you have a question like this 10k you can equate to N1 by N2 the whole square into RL. So like that, if you do, what is N1 by N2 whole square? You have to find the turns ratio of the transformer to match this 16 ohm speaker load. So that will be equal to 10k or 10,000 divided by 16. You will get it as 625. So for matching a 16 ohm loudspeaker speaker to an amplifier circuit with output impedance of 10k, you will have to use a transformer of 625 turns ratio, N1 by N2. This is N1 by N2 whole square. So what is N1 by N2? You have to find out. Sorry, N1 by N2. This is N1 by N2 whole square. What is N1 by N2? If it is 625, then N1 by N2 will be, sorry, I am not able to write it here. N1 by N2 whole square is equal to 625, or N1 by N2 will be root of 625 is 25. 25 by 1 will be the turns ratio. Okay. Now let us discuss about the power considerations which you have to make when you discuss power amplifier. So that this input DC power is given by PI DC and the AC output power is P naught AC plus, then this DC power will be equal to AC output power plus its losses. You can see that this power loss is occurring. Where are these losses occurring? So some of the power losses may occur in the primary of the transformer. So this transformer may have a small finite DC resistance, but usually this resistance is very small, so power loss in the transformer is negligibly small. Then some losses may occur in the core of the output transformer in the form of hysteresis or eddy current loss. This is also quite negligible. Now some DC power is dissipated in RE. That RE drop can also be neglected. Now all these are why? Because all these losses are small compared to the loss that is occurring in the transistor itself. So mainly the transistor loss is considered as the losses, main loss in as far as a power amplifier is concerned. Okay, so why does this much loss occur in the transistor? Because when the majority carriers are made to cross the reverse biased collector junction, so the charge carriers are crossing the junction, some energy is lost and this loss appears as heat. So that is considered as the power loss in the transistor. Okay, so as the collector current and voltage change, as you have larger collector current, these losses will increase in the power amplifier. Okay, now the input power is VCC into ICQ. What is ICQ? The quiescent collector current. So if you consider an amplifier with which is without any distortion, then PI will be equal to VCC into ICQ, which is the quiescent collector current supply from the battery, the average collector current. Okay. Now what is PD? PD is the power that is lost. It will be PI minus P naught, or VCC ICQ minus P naught. P naught is the AC output power. Okay, so this equation is very significant because PD is equal to VCC ICQ minus P naught. It is showing the power that is dissipated in the transistor. We are considering the loss only to be the transistor loss now because we have neglected all the other small losses. So what is a PD max, the maximum power dissipation in the transistor? This occurs when the transistor is not delivering any AC power. So whatever power is drawn from the supply is getting dissipated across the transistor when P naught is 0. So this is the safe power rating of the transistor. So when you want to operate a transistor as in the power amplifier mode, the power rating of the transistor should be equal to VCC into ICQ at least, because it has to dissipate this much power when the AC signal is 0. When it is not handling any AC, PD max will be VCC into ICQ. Okay. Now we can go through certain performance quantities of power amplifier. We'll just get an idea. What is collector efficiency? The main criterion for a power amplifier is not power gain, but it is a maximum AC power output. Now an amplifier converts DC power from supply to AC power. Therefore, the ability of the power amplifier to convert DC power from supply into AC output power is a measure of its effectiveness. This is known as collector efficiency. What is collector efficiency? The ratio of AC output power to the zero signal power or the DC power supplied by the battery of the power amplifier is known as collector efficiency. So this eta will be equal to P0 AC divided by Pi, which is DC. Okay, or P0 divided by VCC, sorry, P0 divided by VCC ICQ. Okay, this is collector efficiency. Now distortion, the change of output wave shape from the input wave shape of an amplifier is known as distortion. And power dissipation capability, the ability of the power transistor to dissipate heat is known as power dissipation capability. Now the classification of amplifiers. Amplifiers may be classified according to where the quiescent point is fixed and how much the magnitude of the input signal is. Based on that, we have different classifications, and the first one is class A. In class A operation, you can see the transistor stays in the active region. This is the similar to the voltage amplifier which we discussed. There is no loss in the output signal or no distortion. You can completely amplify the whole cycle. The transistor is in the active region throughout the AC cycle. The Q point and the input signal are such as to make the output current flow for 360 degrees. So for the whole 360 degrees, this IC is flowing. So this is the operating point here. It is in the middle of the active region, and this is ICQ you have here, which is the ICQ is the quiescent condition collector current. This is the quiescent condition base current. So you can see IB is flowing like this. Then ICQ is flowing for the whole 360 degree, and VCEQ, you can see it is inverted. You are already familiar with this. This is the class A operation of the power amplifier. Next we have class B operation. In this, the transistor stays in the active region only for half the cycle. The Q point is fixed at the cutoff point of the characteristics. The power drawn from the DC power supply by the circuit under quiescent conditions is small. The output current flows only for 180 degree. What does this mean? The Q point is fixed here. So you will be able to reproduce for the 180 degree only, the signal for 180 degree only. The collector current is flowing for 180 degree only. So here you can see IB is like this, but the Q point is fixed here. You are losing some signal here, but the efficiency is more in this class B operation. We will see how we can reproduce this signal completely in class B operation later on, when we discuss push-pull amplifiers. Keep that in mind, but understand that here we have the flow of current for 180 degree only, so half the cycle only. That is what is shown here for class B. The next one is class AB. This operation is between class A and class B. The transistor is in the active region for more than half the cycle, but less than the whole cycle, not up to 360 degree. The output current flows for more than 180 degree, but less than 360 degree. You can see that here. That is, operating point is somewhere here. It is not at the cutoff, but just before that. So, which means you can reproduce the signal up to, or IC will be flowing for more than 180 degree, but less than 360 degree. So, this much signal is only lost. Still, you can reproduce this much. So, that is class AB operation. So, if you consider 360 degree, it is greater than 180 degree, but less than 360 degree. Now, class C amplifier, the Q point is fixed beyond the extreme end of the characteristic. The transistor is in the active region for less than half cycle. The output current remains zero for more than half cycle. The DC current drawn from the power supply is very small. You can see that. The waveform, if you see, the operating point is fixed beyond this. So which means if you have an AC signal which is flowing at the which is given to the input, it is getting amplified for a small period which is less than 180 degrees. So only this much portion of the signal is being reproduced, and for less than 180 degree. That is the property of class C operation. Now, class D is nothing but this the switching operation using the transistor. That is, these are operating either in saturation or cutoff condition. So, this is the input control signal. So, whenever the signal is positive, so here transistor dissipate almost zero power, as in the case of stage A. The voltage is zero or current is zero for the transistors because it is acting as switch. So entire power input is available to the load. So this efficiency of the class D amplifier is very large. Because there is no power which is lost. Either voltage is zero or current is zero as far as this is concerned. So these are designed to operate with digital or pulse type signal, because whenever this base goes positive, so a digital signal is given as control signal like this. Suppose a digital signal. So when it is positive, this transistor will turn on. Then the supply, this V supply will be applied across this load resistance RL. When the input control signal is low, what happens? This is a PNP transistor. You have an NPN transistor here. So this Q1 is acting. Q1 will be in the closed condition whenever the signal is high here. Whenever this signal is high, whenever the signal is low, this PNP transistor will be in the active region. In that case, the output voltage will be connected to the ground. So what happens is, for digitals, as far as digital signal is concerned, when you apply a high and low signal alternately like this, a pulse signal, we are not sure about the time period. We are just trying to understand that these two are acting as switches. So whenever this is class D operation, when these transistors are acting as switch, that is, whenever this is high, this transistor Q1 will conduct and the supply will come across the load. Whenever you get a low here at the input control signal, this transistor will turn on and this will turn off. Whenever this is low at the base of this transistor, this will turn off and this will turn on. So when Q2 turns on, the ground gets connected to the output, or the output will be 0. So this switching operation is known as class D operation, since when the voltage is when this switch is turned on, the current is positive but voltage is across the switch is 0. So in that case, power is dissipated as 0. Whenever the switch is turned off, voltage across the switch is positive but current through the switch is 0. So in that case, again power dissipated is 0. That is why this class D operation is considered to be 100% efficient. So practically, class D amplifiers are designed to operate with digital or pulse type signal. So with this, I'm concluding the discussion on the classification of power amplifiers. You can see for class A amplifier, class B, class C and class AB, the operating cycles we have discussed: 360 degree, 180 degree, less than 180 degree for C, and 180 to 360 for AB. Then Q point position at the center of the active region for class A. Then for class B is on the x-axis, below x-axis for C, above x-axis but below the center of the load line for AB. Like that it goes. Now efficiency is higher for class B, and it is better compared to class A. So we are making use of this property to reproduce the signal without distortion using push-pull amplifiers in class B configuration. Then this is distortion. So distortion is absent in class A. It is present in class B because we are reproducing only half the signal with class B. Then this is highest in class C. Distortion is present in AB also because you are not reproducing the actual signal. So class C operation is never used for audio frequency amplifiers. This is used in special areas of tuned circuits, which is not there in the discussion as far as your syllabus is concerned. So it is used in radio or communications. So with this, I am stopping the discussion on different types of power amplifiers. We'll discuss class A and class B amplifiers in detail in the upcoming lectures. Thank you.